For 233 million years, a piece of rock has been keeping a secret about the weather. In November of 1987, two geologists at the University of Birmingham were doing what geologists do after a long day, comparing notes over drinks, talking shop, half listening to each other the way people do when they think they already know where the conversation is going. One of them, Alastair Ruffell, had spent years buried in a very specific kind of rock called the Mercia Mudstone Group, tracing its layers across Britain. The other, Michael Sims, had been chasing a much stranger problem, a mass die-off of an odd little sea creature called a crinoid, sometimes known as a sea lily, that had puzzled him for months. They weren't working on the same project. They weren't even working on the same kind of evidence. One man had rock, the other had fossils. And then, somewhere in that conversation, something clicked. They were looking at the same moment in time. Buried inside thick red desert sandstone, the kind of rock that only forms when a landscape is bone dry for millions of years, there was a band, gray, streaked with coal, the unmistakable signature of a wet climate, sandwiched inside a desert like a single green photograph in an album of static. And it wasn't just in Ruffell's rocks. It showed up in Sims's data too. Britain, the Alps, the same band, the same moment, over and over, wherever either of them looked. Then, above that band, the desert simply picked back up, as if nothing had happened. Stop here for a second, because what these two men were staring at, without fully realizing it yet, was the fingerprint of the event that would quietly decide who got to inherit the Earth. Somewhere in a hemisphere-sized desert, 233 million years ago, standing anywhere in the heart of the supercontinent Pangaea, you'd have found yourself thousands of kilometers from the nearest ocean, under a sky that essentially never delivered a storm. Red sand in every direction. And then, for a stretch of time longer than the entire history of our own species, that stopped being true. I want to tell you what happened next, but not yet, because the strangest part of this story isn't the rain. It's what the rain did to a group of animals that, right up until that point, were losing. Because right now, in this telling, dinosaurs are not the main characters. They're barely characters at all. The book that sent me down this particular rock face, because that's really what it feels like, descending through layer after layer of stone toward an answer, draws on the work of a geologist named Jacopo dal Corso, who spent years pulling together the modern picture of what Ruffell and Sims had stumbled onto back in 1987. And I'll be honest with you up front, not everything in this story is settled. Some of it is actively being argued over right now, in journals, by scientists who disagree with each other in ways that are still unresolved. I'm going to tell you where the ground is solid, and I'm going to tell you, clearly, where it isn't. Because the shakier parts are, if anything, the more interesting ones. Here's where the ground is solid. Dinosaurs first show up in the fossil record around 245 million years ago. Not with a bang. Not as a triumphant new lineage bursting onto the scene. They show up small, rare, and almost irrelevant. A handful of species scattered thinly across a world that belonged to other reptiles entirely. For more than 10 million years, that's all they are. Background characters. If you'd been able to travel to that world with a checklist of which animal groups were going to inherit the planet, you would not have put money on the dinosaurs. You'd have picked almost anything else. 10 million years is not a rounding error. Put it next to something you can hold in your head. The entire span of time that our own genus, Homo, has existed on Earth is measured in a couple of million years. Multiply that by 5, and you still haven't caught up to how long dinosaurs sat at the margins, doing nothing that looked like the beginning of an empire. Then something changes. And what changes first isn't the animals. It's the sky. Go back to that gray band in the red rock, the one Ruffell and Sims found. For 20 years after their 1989 paper, almost nobody paid attention to it. It sat there, published, mostly ignored, the way a lot of good ideas do before their moment arrives. It took workshops of Italian researchers picking the idea back up in the late 2000s to start asking the question properly. What actually caused a global desert to turn, however briefly, into something wet enough to leave coal behind? To answer that, scientists needed a clock, not a calendar. Nothing so tidy survives from 234 million years ago, but something almost as good. They turned to conodonts. Picture something like a tiny eel, long extinct, that left behind nothing of its body except a scatter of hard, tooth-like fragments in the rock. Those fragments evolved fast enough, generation after generation, that different shapes mark different narrow slices of time, the way growth rings mark years in a tree. Layer by layer, bed by bed, researchers used those fragments, combined with a second technique that reads the magnetic orientation locked into the rock when it formed, to pin down exactly when that wet band began. The answer? About 234.5 million years ago. An interval geologists call the Carnian, itself a slice of the larger late Triassic, and the wet phase inside it didn't last forever. Current estimates put it at somewhere around 1 to 2 million years, hedged because nailing the precise end date turns out to be much harder than nailing the start. Hold that number for a second. 1 to 2 million years of a supercontinent's climate flipping from arid to humid and back, not a storm, not a season, an episode. And that word matters because scientists deliberately avoid calling it a single event, precisely because event implies something short. This was long enough that entire generations of animals lived and died without ever knowing the desert their grandparents remembered. So the next question is the obvious one. What turns on rain for 1 million years across an entire supercontinent? The leading answer takes us somewhere you'd never think to look. A stretch of rock scattered across western North America, British Columbia, and Alaska, so broken up and disguised by time that most people driving through it today have no idea what they're standing on. Geologists call it Wrangellia, a large igneous province, which is a dry name for something genuinely violent. Picture not a single volcano but a wound in the crust itself, pouring out basalt across a huge stretch of the planet's surface, fast enough in geological terms to matter to the whole atmosphere at once. Radiometric dating, measuring the slow clockwork decay of uranium into lead and separately of one form of argon into another, locked inside the volcanic rock itself, puts Wrangellia's eruptions at somewhere between about 232 and 227 million years ago, depending on which method and which samples you're reading. Line that up against the wet episode's start around 234.5 million years ago, and the two windows overlap. Not perfectly. Not with the clean, single-cause simplicity you'd want for a tidy story. The honest version, straight from the researchers who study this, is that a direct link between the volcanism and the specific pulses of rain remains elusive. That phrase is doing real work. It means we think this is the trigger. We can't yet prove the wiring diagram all the way through. But here's why volcanism is still the prime suspect. When you erupt that much basalt, you don't just melt rock. You release gas, carbon dioxide in enormous quantities out of the mantle and into the sky. Estimates suggest that alone could have warmed the planet by somewhere between 3 and 8 degrees Celsius. And a warmer atmosphere is a thirstier one. It holds more water vapor. More water vapor pulled up off a warmer ocean means more evaporation, feeding into Pangaea's existing mega-monsoon circulation, the same seasonal engine that in its normal state barely reached the continent's parched interior. Turn up the heat and the humidity together in a sealed system, and you don't get one changing independently of the other. You get both climbing at once, like someone cranking a stove and a humidifier in the same closed room, somewhere under a shopping mall or a mountain range. In British Columbia or Alaska today, there's basalt that once poured out of the ground fast enough to help do that to an entire hemisphere. And there's a second kind of evidence, one that doesn't rely on dating volcanic rock at all. It comes from the ocean floor itself, and it's arguably the more damning clue. Carbon, as it exists in nature, comes in slightly different weights, different isotopes, physically identical in almost every way except mass. Living things in volcanic outgassing both tend to release carbon that skews toward the lighter variety. So when you drill into seafloor sediment from exactly this moment in time and measure the ratio of light carbon to heavy carbon, you're reading a kind of chemical fingerprint. And right at the base of this wet episode, that fingerprint shows a sharp negative shift, somewhere between 2 and 4 parts per thousand, measured against the standard scientists use to compare these ratios. That's the signature of an enormous pulse of light carbon flooding into the ocean and atmosphere together at precisely the same rock horizon as the coal and gray mudstone. Think about what that means as a piece of detective work. You have gray rock where there should be red. That's the crime. You have a chemical signature consistent with a specific kind of carbon release. That's a fingerprint at the scene. And you have basalt of the right age, half a world away. A suspect with the right alibi gap. None of it on its own closes the case. Together, it's about as strong a circumstantial argument as deep time ever hands you. And it gets stranger because newer work, isotope records pulled from rock in North China, dated only within the last few years, suggests this wasn't one continuous shift at all. It looks more like 3 or 4 separate disruptions spread out across roughly 1.5 to 2 million years, not a single long soaking. More like the ground getting drenched, drying out, and getting drenched again, several times over, across a span longer than our species has walked upright. Try holding that in your head the way you'd hold the difference between one long blackout and 4 separate ones scattered across a week. The total darkness is the same either way, but if you lived through it, the experience would feel completely different. And right now, the scientists studying this can't yet agree on which version actually happened on the ground 234 million years ago. Either way, one long soak or 4 separate ones, something in the ocean was dying while it happened. Something in the ocean was dying while it happened, and the list of casualties is longer and stranger than you'd expect for a climate event most people have never heard of. Conodonts, the same tiny eel-like animals whose tooth fragments gave scientists their clock, took a hit right at this boundary. Ammonoids, coiled shell relatives of squid and octopus that had been thriving in Triassic seas, thinned out sharply. Crinoids, the sea lilies that started this whole story back in Michael Sims's research, suffered losses severe enough that he'd been staring at the puzzle for months before that conversation in Birmingham. Even some bryozoans, small colonial animals that build reef-like structures, and certain kinds of green algae, dropped out of the fossil record at the same horizon. Some researchers, working with data that's only a few years old, have gone further and suggested the scale of this die-off might be large enough to rank among the bigger extinction events of the entire Mesozoic era, the vast stretch of time that includes the whole age of dinosaurs. I want to be careful here, because this is exactly the kind of claim that's easy to let run away from you. It is not textbook consensus. It's a live research thread, argued over in papers from the last several years, not a settled fact sitting quietly in a geology textbook since the 1990s. Some have even called it a hidden mass extinction. Hidden because, unlike the asteroid that ends the dinosaurs' story 30 million years after this one, there's no single dramatic layer of ash, no smoking gun visible to the naked eye. Just a slow accumulation of absences in the rock, noticed only once you know to look for the pattern. And extinction, in this story, is only half of what's happening. The other half is what moves in to fill the space. While conodonts and ammonoids were thinning out, something else was expanding for what looks like the first time. Scleractinian corals, the modern kind, the ones that still build reefs in warm oceans today, start radiating outward into new forms and new numbers right around this same window. So do calcareous nanoplankton, microscopic organisms that build tiny shells out of calcium carbonate and over millions of years pile up into the kind of rock that becomes chalk cliffs. This is not simply a story of loss, it's a story of turnover, one cast of characters thinning out of the play while another steps into the light on the same stage during the same climatic disruption. Now, hold both halves of that side by side. A supercontinent's interior turning from desert to swamp and back, possibly several times over roughly 1.5 million years. An ocean losing some of its most successful groups while quietly building the ancestors of the reefs you'd recognize if you went snorkeling today. And somewhere on land, mostly unnoticed by everyone studying the shellfish and the sediment, a small, rare, marginal group of reptiles is still just sitting there. Waiting, though of course nothing in evolution actually waits. It simply persists, or it doesn't. And only in hindsight does persistence look like patience. I keep coming back to the sheer mechanical strangeness of what a large igneous province actually is, because I don't think the term does justice to the thing itself. This isn't a mountain with a crater on top, occasionally rumbling. Picture instead cracks opening across an area you could drive through for days without reaching the other side. And instead of ash and cinder cones, you get flood basalt, lava thin and fast-moving enough to spread out in sheets, layer stacking on layer, sometimes for what geologists estimate could be thousands of years at a single location before it stops. Each individual outpouring might drown a landscape the size of a small country under solid rock 100 meters thick or more. Do that enough times across enough of the province, and you're not describing a volcano. You're describing a slow-motion resurfacing of part of a planet. And every single one of those eruptions is breathing. Molten rock rising from deep in the mantle carries dissolved gas the way a shaken bottle of soda carries dissolved carbon dioxide. Held in solution under pressure, then released the instant that pressure drops. Sulfur dioxide, carbon dioxide. Over the full duration of a province the size of Rangelia, the sheer cumulative volume of gas released dwarfs anything a single conventional volcano could manage in the same span of time. This is why scientists reach for volcanism first when they see a global carbon isotope shift like the one at the base of this wet episode. Nothing else known to the geological record moves that much carbon that fast, except an asteroid impact. And there's no impact layer here. Just basalt and gas and a very patient signature left behind in stone. Sit with the 3 to 8 degree warming estimate for a moment, because it's easy to let a number like that slide past without feeling its weight. 3 to 8 degrees Celsius averaged across the whole planet is not the difference between a warm day and a hot one. It's the difference between the climate regime your entire evolutionary history was built inside and one your body has never experienced. It's enough to shift where rain falls, how strong the monsoon winds blow, how far inland moisture can travel before it's wrung out of the air. Pangaea's interior wasn't dry because deserts are simply what continents do. It was dry because no ocean was close enough to deliver moisture that far inland, a straightforward consequence of geography, the same logic that makes the middle of any sufficiently large landmass today drier than its coasts. Warm the whole system enough, and you don't just add a bit more rain to the edges. You change how far the humidity itself is willing to travel, and for a window measured in hundreds of thousands of years, it traveled all the way to the center. I find myself thinking about what that actually would have felt like if there'd been anyone there with eyes built for noticing weather the way we notice it. Generation after generation of animals living entirely inside a version of the world their great-grandparents wouldn't have recognized. Rivers running through country that had known nothing but dust. Then, at some point within that 1 to 2 million year window, the rain pulling back, the water table dropping, the desert reasserting itself the way it always eventually does. Whichever version turns out to be correct, one long climatic soak or 3 or 4 distinct pulses separated by drier stretches, nobody alive through any single pulse of it would have known they were living through a global event with a name, let alone one that would still be argued about 250 million years later by people measuring isotope ratios in rock cores. That's the thing about deep time that never quite stops being strange to me. The Carnian didn't feel unified from the inside. Nothing that unfolds over 1 million years ever does to the creatures living through any single year of it. It's only from this end, us holding the whole span compressed into a few pages of geologic record, that it resolves into a single story with a beginning, a climax, and consequences. At the time, it was just weather. Bad weather, strange weather, generation after generation of it, and then, eventually, ordinary weather again. Except it wasn't ordinary, not for what it left behind on land. In 2018, a paleontologist named Massimo Bernardi, working with Jacopo Dal Corso, went looking for an answer in a place most people would never think to check, the Dolomites in northern Italy, where sequences of rock from exactly this window in time are stacked in unusually fine detail. They weren't digging for skeletons, mostly. They were reading footprints. Ichnofauna is the technical word for it, the fossil record left behind not by bodies but by movement. A trackway pressed into ancient mud, hardened into stone, preserving the fact that something walked there at that moment with that stride, whether or not a single bone of the animal survived. And because the Dolomite sequences can be dated with unusual precision, bed by bed, Bernardi and Dal Corso could do something remarkable. Count how common dinosaur tracks were, layer by layer, moving up through time, straight across the boundary of the wet episode. Below it, before roughly 234 million years ago, dinosaur tracks are rare. Scattered. A footprint here, another one several rock layers later, the signature of an animal group that exists but barely registers, the way a minor character might appear for one line in an early scene and then vanish for the rest of the play. Above it, after roughly 232 million years ago, the tracks change. Not gradually, abruptly in geological terms. Suddenly, dinosaur footprints are everywhere in the record, more frequent, more varied, left by more different kinds of animals than before. Skeletal evidence backs up the same pattern. Whatever had kept dinosaurs a marginal presence for 10 million years seems to lift, almost in step with the climate itself settling back into a new configuration. Try to picture what that discovery must have felt like, sitting with that data, watching a line on a graph that had been flat for millions of years suddenly bend upward at almost exactly the same rock horizon where the gray mudstone shows up, where the carbon isotopes shift, where the desert briefly stopped being a desert. That's not proof of cause and effect. Bernardi and Dal Corso themselves were careful about that. A correlation this clean, sitting right on top of a climate disruption this large, is the kind of thing that demands an explanation, but doesn't hand you one for free. The explanation they proposed is what you might call opportunistic replacement, and it's a less flattering story than dinosaurs were simply better. The idea isn't that dinosaurs outcompeted anyone in a fair fight. It's that the animals holding the dominant herbivore niches before the wet episode, certain non-dinosaurian reptile lineages that had been perfectly successful in the old arid Pangaea, were hit hardest by the upheaval in climate and plant life that came with it. Vegetation itself would have been reorganized by a shift this large. The plants an herbivore depends on don't stay the same when rainfall swings from almost none to abundant and back. Whoever depended most narrowly on the old arid adapted flora had the most to lose. And dinosaurs, already present, already surviving on the margins, simply had less invested in the world that was ending. When the incumbents faltered, the empty space didn't stay empty for long. It's worth sitting with how unglamorous that explanation actually is compared to the story most of us grew up with. There's no scene here of a dinosaur outrunning a rival, outsmarting a predator, winning through raw superiority. The proposed mechanism is closer to a forest fire that looks like pure destruction up close, and only later turns out to be the one event that let a particular tree's seeds, the kind that need heat to crack open, finally germinate. Nothing about the fire cared which seeds it was helping. The dinosaurs didn't cause their own opportunity. The opportunity was made by something falling apart around them, and they happened to be standing nearby when it did. But I promised you I'd flag where the ground gets shaky, and this is exactly where it does. Because in the years since Bernardi and Dal Corso's 2018 paper, other researchers going back over the same broader group, Avametatarsalia, the reptile lineage that includes dinosaurs and their closest relatives, have found something that complicates the tidy version of this story considerably. When you measure diversification rate and body size disparity across the whole group, not just dinosaurs narrowly, the rate of change during the Ladinian, the stage right before the wet episode, and the Norian, the stage right after it, both look faster than the rate of change during the wet episode itself. In other words, the group was already diversifying on its own trajectory before this climate event ever started, and kept diversifying afterward at a pace that doesn't obviously owe anything special to the rain. At least one study looking across the whole of the late Triassic found no clear correlation at all between how much precipitation an interval had and how diverse dinosaurs were during it. That's not a footnote you can wave away. That's a direct challenge to the very reading I just walked you through. A serious published disagreement about whether the wet episode actually caused the dinosaur takeover or whether dinosaurs were simply going to keep climbing regardless, and the timing lining up with the climate event is closer to coincidence than causation. I want to be honest with you about where that leaves us. The footprints are real, the timing correlation is real, and the causal story connecting them is genuinely currently unresolved. Some scientists favor it. Others have data that sits uneasily against it. Nobody has closed this case yet. There's a second chemical signature that's entered this story more recently, one that isn't in the older literature Ruffell and Sims were working with back in 1987. And it's worth understanding because of how it corroborates the carbon story from a completely different angle. Alongside the carbon isotope shift, researchers studying rock from this boundary have also measured mercury, not as a curiosity, but because volcanic eruptions, especially eruptions on the scale of a large igneous province, release mercury into the atmosphere in enormous quantities, and that mercury eventually settles out into ocean sediment layered right alongside everything else falling through the water column at the time. Find a spike in mercury concentration at the same rock horizon as the carbon shift, and you've got two independent lines of evidence, built on completely different chemistry, both pointing at the same suspect. It's the geological equivalent of finding a fingerprint and then, separately, a shoe print, both belonging to the same person, both left at the same scene, neither one aware the other existed. This matters more than it might sound like, because a single line of evidence in deep time is always vulnerable to some other quiet explanation nobody's thought of yet. Two independent chemical fingerprints converging on the same conclusion at the same narrow slice of rock is a much harder coincidence to explain away. And it's part of why, even with the causal question about dinosaurs still unresolved, the broader picture, that something volcanic and enormous disrupted the global carbon cycle right at this moment, has held up as more evidence accumulates rather than falling apart under it. I mentioned earlier that this whole line of research sat mostly ignored for about 20 years after the original 1989 paper. I want to sit with that for a second because it's a strange feature of how science actually works, one that rarely makes it into the tidy version of any discovery story. Ruffell and Sims weren't wrong. Their observation held up. But an idea can be correct and still go nowhere for years, simply because nobody picks it back up. Nobody has the tools yet to test it further. Nobody happens to be looking at the right rocks at the right time with the right question in mind. It took workshops of researchers working through the problem systematically in the late 2000s, deliberately revisiting old, half-forgotten data with new isotope techniques that simply didn't exist when the original paper was published, before the picture started resolving into something closer to what I've been describing. An idea can wait in a filing cabinet, correct the whole time, for 2 decades before anyone has a reason to open the drawer again. Now think about what the ocean itself looked like on the other side of this disruption, once the extinction and the reshuffling had both run their course. This is where the reef story becomes, to me, one of the more quietly astonishing details in the whole account. Reefs built by scleractinian corals, the branching calcium carbonate skeletons that still form the reefs divers swim through today, the ones bleaching under modern ocean warming, don't have a long history stretching back before this point. Their radiation, their first real expansion into the reef builders we'd recognize, lines up with this same window. Which means that somewhere in the wreckage of an extinction event, still being actively researched and argued over, in the same disrupted ocean that was losing conodonts and ammonoids and crinoids, the particular architecture of coral reef life that would go on to shape marine ecosystems for the next 230 million years was getting its start. Every reef you've ever seen a photograph of, every clownfish darting through anemone, every diver's memory of color underwater, traces its lineage back through a disruption that also on land was quietly making room for dinosaurs. That's the pattern I keep circling back to in this story, and it's worth naming directly. Destruction and construction, in this record, are not two different events happening near each other in time. They are the same event, looked at from two different angles. The extinction of the old reef builders and the radiation of the new ones aren't sequential chapters. They're two readings of a single chemical and climatic disruption recorded in the same layer of rock, separated only by which fossils you happen to be counting. Let me take you back to the aftermath, once the wet episode's most intense pulses had passed, however many of them there actually were. Above the Julian-Tuvaluan boundary, the substage break inside the Carnian where all of this data converges, the tracks tell a different story than they told below it. Recall that below, dinosaur footprints show up scattered, rare, one print in a rock layer, then a long gap before the next. Above the boundary, in the Dolomite sequences, Bernardi and Dal Corso studied bed by bed the density of tracks climbs, and so does the variety of track makers, not just more dinosaurs, but more different kinds, different sizes, different gaits pressed into the mud at different points in the sequence. If you were walking that ancient landscape with a naturalist's eye, tallying footprints the way a birdwatcher tallies species on a morning walk, the tally sheet from before the wet episode would have a handful of entries. The tally sheet from after would be considerably longer and considerably messier, in exactly the way a landscape looks messier once more kinds of animals are using it. And underneath all of this, holding the whole account together, is a method of measurement that's worth pausing on, because it's easy to take for granted a number like 234.5 million years ago, without asking how anyone could possibly know that with any confidence. Uranium, locked into certain volcanic minerals at the moment they crystallize, decays into lead at a fixed, unchanging rate, not fast, not slow, but constant, the way a very precise, very patient clock ticks whether or not anyone is watching it. Measure the ratio of remaining uranium to accumulated lead in a mineral grain today, and you can calculate, with real precision, how long that clock has been running. A separate radioactive clock, built on one form of argon converting into another, gives an independent cross-check on the same rock. When both clocks, built on entirely different elements, decaying by entirely different physical processes, agree with each other on the age of the same volcanic layer, that's about as close to certainty as deep time ever offers. It's the same principle as the mercury and the carbon. Different chemistry, same conclusion, and the agreement between them is the actual evidence, not any single measurement on its own. There's one more thread in this story, and it's the one that turns this from a strange episode in deep time into something that reaches all the way into your own lifetime. Follow the chain again, slowly, because the chain itself is the point. Step 1, a massive rapid release of carbon into the atmosphere. Step 2, a warmer atmosphere intensifies the water cycle. More evaporation, more moisture in the air, storms and monsoons carrying that moisture further and delivering it harder than before. Step 3, ecosystems built around the old climate get reshuffled. Some groups collapse, others expand into the space left behind. Geological, biological, chemical, 3 completely different kinds of evidence, and they all trace the same 3-step pattern. Rengelia ran that pattern over roughly 1 to 2 million years. It's the only full run of this exact experiment written into stone that we have detailed enough evidence to read start to finish. Carbon spike, monsoon intensification, marine extinction, terrestrial reshuffling, all the way through to a changing of the guard among the animals inhabiting the land. Slow by any human measure. Fast enough in geological terms to leave a scar visible across 2 continents and inside the shells of microscopic plankton alike. Right now, the same chain is running again. Carbon dioxide is being released into the atmosphere by human activity, combustion, industry, the accumulated output of a global civilization, and it's being measured in real time, rising far faster than anything the Rengelia basalts managed, even at their most violent. Not over 1 million years, over centuries. The compression is almost impossible to hold in your head honestly. A process that took the planet somewhere around 1 to 2 million years to run to completion in the Triassic is being attempted by us on a timescale roughly 1,000 times shorter. And the water cycle is already answering the same way it answered then. Warmer air over a warmer ocean means more evaporation. More evaporation means more water available to fall as rain, and it's already falling harder, in shorter bursts, in more places recording measurable increases in extreme rainfall events, while monsoon belts that have held roughly steady for centuries are shifting the boundaries of where they deliver water and where they don't. This is not a metaphor I'm reaching for. It's the same physical chain, the same greenhouse gas, the same intensified water cycle, just running at a pace that would have been, geologically speaking, almost instantaneous. Here's where the pattern gets uncomfortable to sit with, rather than merely interesting. In the Carnian, the incumbents, the dominant reptile groups that had built successful lives inside the old arid version of Pangaea, were the ones whose world came apart fastest, and the group that inherited the vacated space was a minor, marginal one that happened to be adaptable enough, or lucky enough, or simply present in the right place to expand into it. We are not, this time, the equivalent of the dinosaurs waiting quietly on the margins for an opportunity. We're the incumbents. We are the group whose entire civilization has been built around a particular, narrow, remarkably stable climate, the same way those older reptile lineages built their whole existence around a Pangaea that had been arid for longer than anyone alive at the time could have imagined it any other way. I don't say that to be alarmist for its own sake, and I want to be careful here, because the parallel is thematic, not a scientific prediction. Nobody is claiming the Triassic record tells us exactly what happens next, on what timeline, to what degree. But the rock is not shy about what large, rapid disruptions to the carbon cycle have done before. The handful of times something like this has happened at scale. They don't ask the incumbents' permission before they reorganize who gets to thrive and who doesn't. Stand for a moment back inside that late Triassic desert one more time, not to repeat what it looked like, but to ask a different question about it than the one I asked at the very start. It's easy, from this distance, to look at that hemisphere-sized expanse of red sand and think of it as simply barren, a wasted stretch of geological time before the interesting part began. But every square kilometer of that desert was, at the time, exactly as permanent feeling to whatever lived on its margins as the climate you've spent your entire life inside feels to you right now. Nothing about living inside a stable system tells you it's about to end. The only warning, if there ever is one, comes afterward, in rock, long after anyone who could have acted on it has had the chance to. It's worth being precise about something, because it's easy for a story like this to blur into a single vague impression of volcanoes killing things in the Triassic, and that blur would actually erase one of the more important distinctions in the whole record. This wet episode, the one Ruffell and Sims first noticed, the one Wrangellia's basalts are the leading suspect for triggering, is not the event that eventually kills off the dinosaurs. That's a separate story, a separate volcanic province, and it happens roughly 30 million years later, at the very end of the Triassic period, around 201 million years ago. A different set of eruptions, the Central Atlantic Magmatic Province, an entirely different large igneous province from Wrangellia, tied to the breakup of Pangaea itself rather than to this earlier wet episode, triggers what's known as the end Triassic extinction, a larger, later, and more thoroughly documented crisis that clears out much of the remaining competition and opens the door for dinosaurs to move from merely abundant to fully dominant. I raise this now because the two events are easy to conflate, and conflating them would flatten something that's actually more interesting, left unflattened. Dinosaurs don't get one lucky break in this story. They get at least two 30 million years apart from two different volcanic provinces, two different carbon pulses, two different climate disruptions, each one clearing out some fraction of the competition, standing between a marginal reptile lineage and eventual dominance of every landmass on Earth. The wet episode I've been walking you through is the first of those breaks, not the only one, and not the final one. It's the one that gets dinosaurs from rare to merely common. The second one, still 30 million years in this story's future from where we're standing, is the one that gets them the rest of the way. I want you to sit with the scale of Wrangellia itself for a moment longer, because large igneous province is one of those geological terms that slides past the ear without leaving much of an impression, and this one deserves more than that. The fragments of it that survive, scattered and disguised by everything that's happened to the crust in the 230-some million years since, stretch across what's now Vancouver Island, parts of mainland British Columbia, and up into Alaska, a footprint of rock large enough that entire modern cities sit on pieces of it without anyone who lives there necessarily knowing it. That's not a volcano you could stand at the base of and look up at. It's a landscape-scale event, one that unfolded across an area you'd need days to drive across, laying down basalt in sheets that in places run for what would have been, at the time, an almost unimaginable thickness, event after event, over a span radiometric dating puts at somewhere across roughly 6 million years from earliest to latest phase, a range built from the uranium-lead and argon-argon estimates on either end. And somewhere inside that broader multi-million-year window of eruption, a narrower slice, the part whose timing overlaps most closely with the wet episode's onset around 234.5 million years ago, is the part doing the work in this story. Not the whole 6 million year history of the province, just the early pulses, the ones whose gas output happened to coincide with the moment the rock record shows the desert turning wet. That's an important qualification, and it's part of why researchers are careful to call the volcanic trigger a leading hypothesis rather than a proven mechanism. Matching up the right slice of a multi-million-year eruptive history against a narrower 1 to 2 million year climate disruption is a harder, more precise kind of dating than simply confirming the two things happened somewhere in the same rough era. This is also, I think, where the ongoing nature of this research becomes most visible and most honest. This isn't a discovery that closed in 1989 or even in 2018 when the dinosaur footprint data came out. Between roughly 2020 and the last few years, teams working on isotope records from North China and from Tethyan sections, rock laid down in the ancient sea that once separated the northern and southern halves of Pangaea, have been actively refining exactly how many distinct pulses this event contained, whether it's 3, whether it's 4, whether the whole 1 to 2 million year window needs to be understood as one continuous disruption with internal noise, or several genuinely separate, briefer disruptions with real gaps of ordinary climate in between. That question is not resolved as of this telling. It's being worked on right now by scientists pulling core samples out of rock formations on opposite sides of what used to be one ocean, checking whether their separate datasets agree with each other closely enough to settle it. I find something genuinely moving in that, more than I expected to when I first came across this story. 250 million years after the fact, human beings are still out in the field, still drilling into stone, still arguing in good faith over exactly how many times it rained on a desert that no longer exists, populated by animals none of us will ever see alive, because the answer might tell us something true about how fast a planet's climate can be pushed off one stable state and into another. Nobody doing that work will ever get to see the event itself. They're reconstructing a multi-pulse storm system from chemical residue in rock, the way you might reconstruct the shape of a room you've never entered from nothing but the echoes bouncing back out of it. Go back, for a moment, to the physical texture of that original discovery, because I skipped past something worth dwelling on. What coal actually requires to form. Coal isn't just wet rock. It's compressed plant matter laid down in swamps or bogs thick enough with vegetation that when it died, it piled up faster than it could fully decay and got buried before the world could finish breaking it down. Which means that gray band Ruffell and Sims found sandwiched inside red desert sandstone isn't merely evidence of rain falling on dry ground. It's evidence of standing water, of vegetation dense enough to form peat, of an ecosystem completely foreign to the desert immediately above and below it, full swamp forest, for a geological instant, inside the driest interior of the largest landmass that has ever existed. That's the detail that made the 1989 discovery so startling to begin with. Not damp sand. An entire wetland ecosystem complete with the biomass to leave coal behind, embedded like a fossilized wound inside rock that spent millions of years on either side being unable to support anything of the kind. I think of it now the way you might think of scar tissue inside a tree trunk. Cut a cross-section through an old oak, and you'll sometimes find a dark ring where the wood remembers a single injury. A fire, a lightning strike, an insect infestation, one bad year decades or centuries ago, preserved permanently inside growth that otherwise looks uniform. The tree didn't stop growing normal wood before or after. It just carries, forever, this one legible interruption, dated precisely by counting the rings on either side of it. The gray band in the Mercia mudstone is that same kind of scar, except the tree, in this case, is an entire supercontinent, and the growth rings on either side of the injury are made of hundreds of meters of red desert sandstone rather than wood. And just as you can date a tree's scar by counting rings outward from it, researchers dated this one using something that functions almost exactly like a calendar, except it predates trees as anyone would recognize them today. The conodont fragments layered through the rock, changing shape in a fine, traceable sequence as you move up through time, work as their own kind of ring count, not annual, but fine enough and well enough calibrated against the radiometric dates from Wrangelia's basalts to place this scar with real confidence at roughly 234.5 million years ago. What made the crinoid puzzle Michael Sims was chasing so genuinely strange, before that 1987 conversation connected it to anything else, is worth returning to now that you have the fuller picture. Crinoids, animals that look almost like flowers with a stalk anchoring them to the seafloor and feathery arms filtering food out of the water, had been a stable, successful part of Triassic marine ecosystems for a long stretch of time before this. Their sudden, significant thinning out at this particular boundary didn't, on its own, point to any obvious cause. Nothing about a sea lily's biology screams climate change on a distant continent. It took setting that marine data down next to Ruffell's terrestrial rock, two completely unrelated fields of study, brought together only because two researchers happened to be comparing notes over drinks, before the crinoid extinction stopped being a mystery in its own right and became one line of evidence inside a much larger, planet-spanning story. That's worth remembering the next time you hear about some isolated, unexplained die-off in the fossil record. Sometimes the explanation isn't hiding in the data you're already looking at. It's sitting in a completely different researcher's notebook on a completely different continent, waiting for the right conversation to happen. By the time Jacopo Dal Corso came to synthesize all of this into the 2020 paper that ties the wet episode directly to the origin of dinosaurs, he wasn't working from a single line of evidence any more than Ruffell and Sims had been in 1987. He was pulling together conodont-dated rock sequences from Britain and the Alps, radiometric ages from basalt fragments scattered across western North America and Alaska, carbon isotope curves from marine sediment cores, mercury spikes from the same cores, and now, layered on top of all of that, the footprint and skeletal data Bernardi had assembled from the Dolomites. None of those data sets on their own could have supported the full account. It's the fact that they all independently converge on the same roughly 234 million year old horizon, measured by completely different methods in completely different kinds of rock across two different continents, that makes the synthesis as strong as it currently is, while still, honestly, leaving the sharpest causal question, whether the rain specifically is what handed dinosaurs their opportunity, unresolved. That unresolved question is, I think, the most honest place this story can sit, at least for now. Not because the uncertainty is a flaw in the science, because it's exactly what real science looks like while it's still being done, before it's calcified into the version that eventually makes it into a textbook, stripped of its hedges and its disagreements, presented as though it had always been obvious. What you've been hearing is the version before that calcification. Researchers on different continents reading different rocks, some of them convinced the wet episode was the decisive break for dinosaurs, others holding data that says the diversification trend was already running on its own regardless. Both sides working from real measurements, neither side yet with enough to force the other to concede. There's an image I keep returning to for what dinosaurs actually were, for those 10+ million years before any of this happened, and it's worth spelling out fully now that you have the whole chain of evidence behind it. Picture an understudy who's been in a production for years, never once stepping into the lead, watching the same handful of headline performers command every scene, night after night, show after show. Nobody's cutting the understudy from the cast. They're still there, still capable, still occasionally getting a line. But nobody watching the play would tell you their name afterward. Then, for reasons that have nothing to do with the understudy's own talent, the production itself is disrupted. The lead performers who'd built the whole show around a certain kind of stage, a certain lighting, a certain set, a certain house style, the equivalent of a specific arid climate they'd spent generations perfecting themselves for, find that the production they trained for no longer exists. The understudy is still standing there, unchanged when the curtain goes back up on whatever comes next. That's the honest shape of the leading hypothesis, stripped of any language that makes it sound like dinosaurs earned anything. They didn't out-evolve the incumbents. The stage changed under everyone at once, and they were simply still standing when it stabilized again. It's worth asking, even knowing the answer can only ever be speculative, what the following 165 million years might have looked like if Wrangellia had never erupted, if that particular 1 to 2 million year climate disruption had never reached the interior of Pangaea. Nobody can run that experiment. The rock only records the version that actually happened. But the honest implication of the diversification rate data, the finding that evemitted Arsalians were already climbing in the Ladinian, already climbing again in the Norian, is that dinosaurs may well have found their way to dominance eventually, regardless, just later, by some other route, through some other disruption, on some other timeline none of us will ever get to check against. The wet episode might not be the reason dinosaurs eventually ruled the Earth. It might simply be the reason they got there when they did, rather than some later moment lost to a version of history that never happened. Either way, the rock underneath your feet, wherever you happen to be standing right now, carries some version of this story in it, whether or not it happens to be the specific red sandstone or gray mudstone this account has been built from. Every layer of stone anywhere on this planet is doing exactly what the Mersha mudstone did, quietly recording the only version of events that actually occurred, indifferent to whether anyone would ever come along, 234 million years later, curious enough to read it. Take a breath. Feel the air move in and out of your chest, ordinary, unremarkable, exactly the way it's supposed to. Somewhere back in a rock face in Britain, there's a band of gray a few inches thick, pressed between hundreds of feet of red desert stone, and it is, by every honest measure, mostly just proof that it rained. That's all it is, and it's also the reason you're the species sitting here listening to this, rather than something else entirely. Every dinosaur that ever lived, every skeleton standing in every museum hall, all 165 million years of that dominion, the asteroid that eventually ended it, and the small, quick mammals that filled the silence afterward, including, eventually, us. All of it may trace back through a scar in the rock that says nothing more dramatic than, for a while, on a desert the size of a hemisphere, it stopped being dry. Nobody living through it knew they were living through anything. It was just weather, and then it was ordinary again, and the world it left behind quietly became this one.